3.4, those of you who like to label. Okay, we're going to talk about 3.4 today and tomorrow. Okay, so concavity describes the curvature of our function. We are going to describe that our function is either concave up or concave down. Okay, so we've been talking about increasing and decreasing intervals. But now I will also ask you to identify intervals of concavity. Where is your graph concave up and where is your graph concave down? Okay. Will a line have concavity? No, because it's straight. Okay. But anything that curves would be either concave up or concave down. Okay. This right here is a concave up graph. This right here is a concave down graph. Okay? If we are concave up, then we could hold water. If we're concave down, then the water's going to spill, kind of like a cup. If you hold it up, it stays in. If you turn it over, it all falls out. Okay? Now, our second derivative is what is going to help us figure out our concavity. Okay. So F prime tells us how the y values of the graph are changing, right? We're talking about change of y over change of x. Our second derivative is telling us how the slopes are changing. So since the second derivative is the derivative of the derivative, then we're talking about how is the change of the change. Okay. So first derivative represents our slopes. So our second derivative is talking about how are our slopes changing. This is a graph that is always concave. What? Down. Okay. Let's talk about the slopes. As I look at the slopes, what's happening as we go from left to right? What's happening to these slopes? They're getting smaller. Here they turn to 0, and we go in the negative direction, but as we continue, what's happening with our slopes? They're still getting smaller, okay? So our slopes are getting less steep. We could say our slopes are decreasing, okay? Okay. Let's talk about this concave up picture. Okay, as we go from left to right, what's happening with our slopes? They're getting bigger, right? So they start pretty negative, and as we continue left to right, our slopes get bigger and bigger and bigger and bigger in numeric value, okay? We could describe it as our slopes increasing. Okay, so if concave down means our slopes decrease, and concave up means our slopes increase, okay? Do you remember when we talked about increasing and decreasing intervals, we looked for where the derivative was positive versus negative. Okay. Well, now I'm concerned about where our slopes decrease and increase. So in order to determine concavity, we're going to look at the second derivative. So if we have a second derivative that's positive, that means our function is concave up. Okay? If our second derivative is positive, that means our first derivative is increasing, which means our function is concave up. I would write all of that down because we are going to put that all together numerous times. Concave up means slopes are increasing, which means our second derivative is positive. Vice versa, wherever our second derivative is negative means we are concave down because our slopes are decreasing. And if our slopes are decreasing, then that derivative is negative. Now, is it possible for a second derivative to be 0? Okay, and that just means we have no curvature. There's no concavity there. Okay? If the second derivative is 0, then at that point your slopes aren't changing. Okay? We're going to talk about what it leads to here in a moment. Okay? It's also possible for your second derivative to be undefined. Okay, and we'll talk about both of those cases because I bet, just like the first derivative, they could tell us something. Okay. Now, when we had moments of increasing and decreasing, when it changed from increasing to decreasing or decreasing to increasing, we talked about extrema. We talked about our relative minimums and our relative maximums. Okay. When concavity changes, it's also something we need to be able to point out, okay? It's not as intense as minimums and maximums, all right? However, we still need to know. So when our concavity changes, okay, so do you see how this picture goes from concave up to concave down? This is what we call an inflection point. You'll hear me say point of inflection or inflection point. Okay? An inflection point means our concavity is changing. What?
For some reason my heart is fat now. I can't write that down.
So an inflection point is where our concavity changes. What do you think the second derivative should equal there? Or? Okay, just like a potential minimum or maximum, right? Inflection points occur when the second derivative is 0 or undefined. Now, just like with our critical numbers, did every critical number turn into a minimum or maximum? It did not. So we're going to identify places where the second derivative is 0 or undefined, but that doesn't mean it's going to be an inflection point. Okay? Let's maybe look at some pictures. Okay. So how about you just put your pencils down for a moment, and we'll just really just take it in together, okay?
Bless you.
Okay. All right, so here we go. At P, we have an inflection point. We change from concave down to concave up. Here, our second derivative would be 0. Okay. Here, do we change concavity? This is concave up, and this part is concave down. Do you see that change where this is cupped up and this is cupped down? Okay, so here point P is an inflection point. What would the second derivative be here? It'd be undefined because of that corner, okay? But it's still an inflection point because we change concavity. Now, here's an example of a time where our second derivative is undefined because of the corner. However, does it change concavity? It stays concave up, concave up. So this would not be a point of inflection, and that's okay. All right? Another time where we maybe wouldn't see a point of inflection is something like this. Okay? This part of the graph is concave down, but this part of the graph is concave up. We see a change in concavity, but we have an asymptote. So P isn't a point of inflection, but it does break up our intervals of concavity. Okay? At an asymptote, our second derivative would be undefined, so we'll still identify it, but we can't call an asymptote a point of inflection, okay? Because it's not a point. So what we're going to do moving forward, we're going to do a few algebraic examples, okay, of how to figure out where a function is concave up versus concave down, and how to identify a point of inflection. All right, so we'll start off nice and easy for you. We love polynomials, right? Okay, so our first derivative, what would it be? And if we wanted to do minimums, maximums, increasing and decreasing, then we could set this equal to 0 and move forward, right? But we care about concavity. So let's find the second derivative. What's the second derivative? 6x. All right. So our second derivative we have, and just like with the first derivative, we want to know where it is 0 or undefined. Where does that happen? Okay, x equals 0. Cool. I am going to label my number line with f double prime because I am concerned about the second derivative and where it is positive versus negative. All right. So if we plug in a number to the left of 0, what kind of value is my second derivative? Negative. If I plug in a number to the right of 0, what kind of number is my second derivative? Okay. So we have a curve that is concave up from 0 to infinity. It is concave down from negative infinity to 0. Since we have a change in concavity, POI, point of inflection. Okay, that's just my shorthand for it. Since we have a change of concavity, we have a point of inflection. And our inflection point is occurring at x equals 0. If I want the actual coordinate, where do we throw 0? Into the original equation. So 0, negative 4 is our point of inflection, or our inflection point. I don't care what you call it. Okay. What do you think? That's right?
No.
Okay. I am going to skip an example and go to this one right here. Nope, not this one. I changed it. F of x equals x to the 2/3. And we're going to look at increasing and decreasing and concave up, concave down. Okay? Okay. Now, let's talk about increasing, decreasing. So this is what we did yesterday and the day before. What is our first derivative? 2/3 x to the negative 1/3. Right? Okay. Now, we like to rearrange that as 2/3 x to the 1/3. Right? Okay, what would our critical numbers be? Where is our derivative equal to 0? Nowhere. Where is our derivative undefined? At 0. Okay. And this is where it really becomes important. If I'm going to talk about increasing and decreasing and then talk about concavity, I need to label my number lines. So I have my number line labeled with x is 0. If we plug in negative numbers, what kind of derivative do we have? We would have negative numbers, right? Okay. And if I plug in anything to the right of 0, we would have positive numbers. Okay, so from this we know that we are increasing from 0 to infinity. We are decreasing from negative infinity to 0. And we would have a relative minimum at x equals 0. I'll let you know that the y coordinate is 0. So we're increasing from 0 to infinity. We're decreasing from negative infinity to 0. And we have a relative minimum at 0, 0. Okay. Now, let's be strategic about this. If I want to know about concavity, then we need the second derivative. Well, do you want to take it from this right here? No. Let's come back to this unsimplified version, right? And let's take the derivative from here with the power rule, okay? So when we do the power rule, we would get negative 2/9 x to the negative 4/3. Good. So then we can rewrite our second derivative to be 2/9 to the 4/3. Negative, because that is a negative before. So now, same thing. Where is our second derivative? 0. Well, nowhere. But our second derivative is undefined at 0. Sometimes that happens. Not very often. where our critical numbers and our potential inflection points are the same, but today, this example it is. Okay? Now, do you see how I labeled my second derivative number line? Okay? That means we're testing values in our second derivative. So to the left of 0, if we plug numbers here into our second derivative, what kind of numbers do we get? So like -1. -1 to the 4th power is going to be positive, right? Which means this entire fraction would be negative. Okay? If I plug a number in over here, like 1, x to the 1 to the 4/3 in all of this, this would also be negative. Thank you. Okay. So we are concave down. I do want you to write this as negative infinity to 0 and 0 to infinity. I do want you to break it up. Because at 0, technically, do we have concavity? We don't. Okay. Do we have a point of inflection? No, because we don't actually change our concavity. What's happening, it looks like this. Looks like a bird. Right? This is how you used to draw birds. Okay, so drop your pencils. We're just going to talk about this graph together. So this is a graph of the derivative, right? If I were to ask you where our function is increasing, we would pick out which interval? This is the derivative. So we would pick out 1 to 6 and we'll say 8 to 9 because it kind of stops there. Now, what about if I want concave up? So this is the derivative, right? Concave up means our slopes increase. This is the derivative, meaning slope. Where is the slope increasing? 0 to 2. And 3 to 5. Whoops. And 7 to 9. Where, that's a 7. Where the derivative is increasing, that means our next derivative is going to be positive. Okay. We're going to do, since I'm not here tomorrow, I don't want to leave a pink sheet for, like this pink sheet that we did yesterday. I have one that involves concavity also, but since I'm not going to be here, I get nervous about leaving it. So we'll do it either Monday or Tuesday where we're going to do all of this with the concavity involved. Okay? So your homework is, I think, mostly just algebra with find the second derivative, find where it's negative and positive so you can pick out concave up, concave down intervals and points of inflection. Tomorrow you will learn what's called the second derivative test, where you use the second derivative to find minimums and maximums. Okay. All right. If you're not here tomorrow, there'll be a video on my website for you to watch.